Can an algorithm stop a billion-dollar disaster before the first crack appears? Traditional structural codes are static snapshots. We only check a bridge's health every 2 years. But today we are moving to dynamic, real-time data. It's the difference between a single photograph of a patient and a live 24/7 heart rate monitor. We are no longer just designing for the worst-case scenario on paper. We are listening to the structure's pulse as it happens, using thousands of data points to foresee trouble before it even starts. To predict a disaster, we need sensors. Modern infrastructure is now equipped with a nervous system of sensors, accelerometers, strain gauges, and piezometers. These sensors pour massive amounts of information into machine learning algorithms. Think of these algorithms as a highly experienced engineer who has seen 1,000,000 bridges. They process noise, vibrations, and temperature shifts to find patterns that the human eye would miss, like the one we discussed in the previous video, or a tiny, repetitive tremor that signals a fatigue crack forming deep within the steel. But there is a catch. Most AI models are what we call a black box. You give them data, and they give you a prediction, but they don't tell you why. In civil engineering, because the computer said so isn't enough to justify closing a multi-billion-dollar highway. If the AI predicts a collapse but can't explain the physical mechanism behind it, we face a crisis of trust. We cannot risk human lives on a statistical guess that ignores the laws of gravity and material science. The solution is brilliant: physics-informed neural networks, PINs. Instead of letting the AI just look at numbers, we bake the laws of physics directly into its brain. We feed it the Navier-Stokes equations or the Euler-Bernoulli beam theory. This way, the AI must obey the conservation of mass and energy. It's like giving a calculator a soul that understands gravity. Combined with explainable AI, XI, we can now see the reasoning. The AI can point to a specific stress concentration and say, I predict failure because the shear force exceeds the material capacity here. One of the toughest challenges is geotechnical engineering. Soil is notoriously unpredictable. But by applying predictive AI to slope stability, we can analyze rainfall patterns, pore water pressure, and soil displacement in real time. The AI acts like an early warning system for landslides. It doesn't just say a landslide might happen. It calculates the factor of safety dynamically as the storm hits, giving engineers precious hours to evacuate or reinforce the area. In skyscrapers and bridges, we use structural health monitoring. AI scans the data for anomalies. Imagine a skyscraper during an earthquake. The AI can instantly determine if the building's stiffness has changed, indicating hidden internal damage. This moves us from reactive maintenance, fixing things after they break, to predictive maintenance, fixing things because the AI detected a microscopic change in the structure's vibration frequency. But who is responsible when the AI makes a call? The American Society of Civil Engineers addressed this in Policy 573. The bottom line? AI is a tool, not a replacement for the professional engineer. The engineer remains the final authority and holds the ethical and legal obligation to protect public safety. We use AI to augment our judgment, not to outsource our responsibility. As engineers, we must understand the limitations of the algorithms we use. We are the pilots, and AI is our advanced autopilot. Here's the cold truth. AI is only as good as the data it eats. In civil engineering, we have a massive problem: data availability. Unlike the internet, we don't have billions of bridge collapses photos to train our models. Most of our data is healthy data, which makes it hard for AI to recognize unhealthy patterns. How do we get the data we need without waiting for disasters to happen? That is the billion-dollar question we will explore in future videos. We'll reveal how we use synthetic data and physics-informed models to solve this data hunger. If you are a fellow researcher or engineer looking to build a stronger technical foundation, subscribe and join the discussion below. This is the Strong Foundation Engineering, and I'll see you in the next deep dive. Stay tuned.